These are Notes 2.5, piecewise functions. You may or may not have had this in the past, so it could be new for you. A piecewise function basically just means we're going to use this function for certain x's. They're going to use this function for other x's. A real life example of this would be, let's say that you're working and you make $10 an hour. Okay? So if you think about working $10 an hour, if these are the number of hours that you work, you know, after 1 hour you make $10, right? After 2 hours you would make $20. Okay, so you have this function here. Now, once you get up to 40 hours though, in a job, okay, 40 hours at $10 an hour would be $400, right? Okay. After 40 hours, people make something called time and a half. So they make their $10 an hour plus half of that, so they actually start making $15 an hour. So at 41 hours, they would actually be making, they wouldn't go up 10 anymore, it'd go up 15 and over 1, so it becomes steeper. So this is an example of where we have one function up to a certain point, it's like 40, and then we have another function that takes over for that after that point. Okay? So if we look at this first example, x plus 2, okay, for all of our x's that are less than or equal to 0. Okay, so 0 or less than that. Okay, so we're looking at over on this side over here. Not over here, just at 0 and less than 0, we're going to use this function. Okay, so how do we graph that? We start at 2, and our slope says we go up 1 over 1, but I don't really want to be on this side, so I'm going to go down and left, and down and left, and down and left. So I have that graph right there. Okay, but notice I'm only using it for the x's that are 0 or less than 0. Okay. Now it says we're equal to as well, so that's filled in there. Okay, so then this one, y equals 1/2 x squared, we're going to use for greater than 0. So let's say at 0, if I plug a 0 in here, 0 squared is 0, half of 0 is still 0, so that's down here at 0, 0. Plug in a 1, 1 squared is 1, half of 1 is 1/2. Let's plug in a 2, 2 squared is 4, half of 4 is 2. Plug in a 3, 3 squared is 9, half of 9 is 4.5. Okay, so it gives you an idea. We know this is a parabola, so it gives us this graph there, and since this is not or equal to, this is an open circle right there. Okay, so there we have our graph. Now, to get the graph as well, if you're not sure what these look like, feel free to go to Desmos and graph y is equal to x plus 2, and then you can move your cursor at different points and see what that looks like. Then you can also put that y equals 1/2 x squared, and that'd be, you can get those points through just clicking on Desmos. I will also, at the end of this video, add on a section about Desmos of how to graph these on Desmos. You can actually type this whole thing in to make sure your graph is correct. Okay, I'd like you to try to do it by hand though too. Okay, f of negative 3. So if I want to know f of negative 3, do I use this function or do I use this function? Well, my x there is less than or equal to 0, so I have to use this function. So it'd be negative 3 plus 2, which is negative 1. Okay, and you can see that here. F of 3 is equal to negative 1. Okay, f of 0. Okay, it's not greater than, but it is or equal to 0, so we're going to use the top function. So it'd be 0 plus 2 is 2. Okay, so we have that point right there. F of 3, okay, no, f of 3 doesn't use this function, it's greater than 0, so we're going to use this function. So it would be 1/2 of 3 squared, so it would be 9, 4.5, so that point right there. Okay, I'd like you to pause it and try this by yourself. Okay, so we're going to have this equation here. Get a pencil to use. So if I think about this equation right here, you know that it starts at 1 and it has a slope of up 1 over 1, right? So we have a graph that would look something like this. But we're only going to use it for x's that are less than or equal to 2. Okay, so I'm just going to draw a little line there. So at 2, I'm going to use this graph on this side, right? So it's slope, y-intercept is 1, up 1 over 1, okay? So I'm using it on this side, okay? Less than 2. Okay, now, between 2 and 4, we're going to use the line y equals 3. Y equals 3 is just a straight across line. Okay, y equals 3 goes like this, but we're only using it from 2 to 4. And then we have this other equation, which would start at 7 and go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, okay? But we're starting it over here. We're not using it over here, we're just going to use it on this half over here. So it's going to go somewhere like this, right? So let's actually find the points. So at 4, negative 2 times 4 is negative 8. Negative 8 plus 7 is negative 1. So I have the point 4, negative 1. Okay, and that would be an open circle because it's not or equal to. Okay, let's go to 5 then. Be negative 10 plus 7 is negative 3. And we can go to 6. We know it's a straight line, so we could just draw this, but one more that won't hurt. So negative 12 plus 7 is negative 5. Okay. So you have that line right there. Okay. This one was or equal to right there, and since these meet, that's just a point there. Okay, so that's your graph there. Once again, I'll show you at the end of the video how to do this in Desmos as well. So f of 4, which one do I use? Okay, it tells us or equal to 4, so I'm going to use this one. So I know it's equal to 3. F of 100, it's not less than 2, it's not between 2 and 4, but it's greater than 4. So I have to use this one. So negative 200 plus 7 would be negative 193. Okay, f of 2. Okay, no, yep, we're equal to 2, so I have to use this one. Okay, so there is how you work those out. Okay, so this one here, now we want to write the actual function for this. Okay, so let's create the bounds first. Okay, so here is our bound, right, at 1. So we're going to use this equation for the numbers less than 1 or equal to 1, right, because it's still filled in. And on this side is for our x's that are greater than 1. Okay, so 1 greater than 1 and less than 1. Okay, so this equation here has a y-intercept of 0, goes up 1 over 1, slope of 1. So it's just y equal x. This one here looks like your slope goes down 1 over 1, down 1 over 1. So negative x, and the y-intercept would be up there at 3. Okay, so that would be your function there. Okay, I guess you don't really need that at the end. Okay, this one here. Okay, so let's look at our bound. Our bound here is at negative 1. So we're going to use this function for our x's that are less than negative 1. I'm going to use this function for our x's that are greater than negative 1. Notice the open circle, so nothing is or equal to a negative 1 there. Okay, so let's take this equation here that has a y-intercept of 2 and a slope that looks like it goes up 1 over 1. So it would just be x plus 2. And then this equation here looks like it has a slope that goes down 1 over 3. So negative 1/3 x. And the y-intercept would be, if it goes down 1 over 3, then if it goes over 1, so it's going to be at 1/3 there. 1 1/3, or 4/3. Okay, so that's how you write that equation there. So piecewise functions can be a little confusing, so if you need to watch this video over a couple times and to figure it out, please go ahead and do that. Okay. Okay, the next function is something called a greatest integer function. The greatest integer function uses these double brackets. Okay, that's how you know it's a greatest integer function. And it's also a type of piecewise function. If x is an integer, okay, so remember what integers are, like -1, -2, 0, 1, 2, okay, etc. Those are integers. If it's an integer, then my function is just the integer. If it's not an integer, so if it's any decimals in between here, we go to the greatest integer that is less than the x. Okay, so for example, f of 4 in my greatest integer function would just be, 4 is an integer, so the answer is just 4. Okay, f of -5 is an integer, if my answer is just -5. f of 2.46, okay, so it's not an integer, So we're going to go to the next integer that's less than x. Okay, so if this is my x, the integer that's less than this would be 2. Okay, pi is 3.14, not an integer. Go to the number that's less than x, which would be 3. Okay, negative 6.5, not an integer. The one that's less than this, be careful there because it's negative. Think about a number line, negative 6.5, right? The number that's less than that would be negative 7. Okay, so what does that look like as a graph? Okay, so we think about this here. Basically anything from 0 to 1, okay, not including the 1, but any decimal here would go to the lower one, which would be 0. Anything from 1 to 2 would be 1. Okay, so including 1 would be 1. But once you get to 2, 2 jumps up to the next one, to 2. So the graph kind of keeps jumping like this. So if it's an integer, if it's a number in between, it goes to the lower number, right? It goes to the lower one. And you can do the same thing with your negative numbers there too. Okay, so that's what the greatest integer function looks like. Kind of an idea of this is if you have mail, right? And I'm not sure what the prices are, but if you have a certain weight to the mail, you get charged a certain price up to that weight, and then it jumps to a different weight, and you have to go to a different cost for that. And once it jumps to a different weight, they have to have a different cost for that. So that's sort of an example of that. Okay. So here we have the greatest integer function of 1/2 x plus 1. So let's make a little chart of this. Okay. So let's say x is 0. So let's plug in the 0. Half of 0 is 0. 0 plus 1 is 1. Plug in the 1. Half of 1 is a half. A half plus 1 is 1.5. The greatest integer, the one less than that, would be at 1. Plug in the 2. Half of 2 is 1. 1 plus 1 is 2. So that's an integer, stays at 2. Okay, try and think about what 3 would be. Half of 3 would be 1.5. Plus 1 more makes 2.5. So at 2.5, the one less than that would be at 2. Okay, and you can kind of see that pattern here. So basically, at 0, it's 1. And then at 1, it's 1. And at 2, it turns to be 2. But anything below 2 would still be here, right? So we'll just put an open circle there. But at 2, it jumps to 2. And then at 3, it's still at 2. And at 4, it would jump to 3. Okay, so you can see that function, and you can figure out some of the others too. Okay, let's think about, I didn't think about this here, domain, range, etc. Our domain, okay, so are there any numbers that don't work to plug into here? Right? If I plug in this value there, I get there, I get there. Any value works, because if there's an open circle, there's a closed circle then. So our domain goes from all real numbers. The range, okay, so in range, we don't have any decimals, do we? All of our outputs, all of our ranges are integers. Okay, so the integers are what the range is. There's no decimals in there, because it always goes to the lower one. Is it continuous? Yeah, definitely not, because we have to lift our pencil to get to the next one. Okay, so here the domain, once again, this would, keep going for all these numbers here, so it would be all real numbers. And the range would, once again, we have every integer. Okay, now if I'd had, yeah, so we'll leave it at that. Okay. Okay, next here, word problems, you guys love these. So downtown parking, let's say they charge $5 for a base fee for parking for 1 hour. And then they charge another $1 for each additional hour or a fraction of that hour. So if you're there for an hour and a half, you pay their base plus an additional $1 for that hour. The max fee for 24 hours is $15. So you're not going to be charged more than $15 over a 24-hour period. Okay? Okay, so this is the hours, and this is how much we're being charged. Okay, so as soon as you get into the parking garage, you are charged $5, right? Okay, so anywhere from 0 hours all the way up through 1 hour, you're charged $5. Okay, now at 1 hour to 2 hours, you're charged that $5 plus an additional dollar. So you would then have to jump to $6. And then from 2 to 3, you would have to be charged $7. Okay, and 3 to 4, you would be charged $8. Okay, so you can see how this keeps stepping up another dollar for every hour. Okay, let's think about what happens out here at 15 though. Okay, I'm sorry, not 15 there. When it reaches 15 here, okay, so let's think about how many hours where that would be here. Okay, so when does we reach 15? So we had $5 here, right? And then $6, and then $7, and $8, 9, 10, 11, 12, 13, 14. Okay, and then here it reaches $15, right? So we know at 11 hours it reaches $15. And then after that, all the way up through 24 hours, we're just charged a base of $15. It's never going to go above that for a 24-hour period. Okay. Next one, due to acid rain, the percentage of lakes in Scandinavia have lost their population of brown trout. I guess the brown trout increased dramatically between this year and this year. Based on the sample, this is the model for the brown trout in Scandinavia. Okay, so we're going to use this model for 1940 to the 1960s. We're going to use this model for all of our from 1960 to 1975. So what they're noticing is it has a certain model between 1940 and 1960. There's a certain percentage of increase, not as much though. And then after 1960 to 1975, they saw a different increase, a different formula take up. Okay, so what is the percentage in 1950? So 1950 would fit in this category. So we got to plug that in here. So 11/20, 1950 minus 1940 plus 7. And if you work this out here, it comes up to be about 12.5%. Okay. And then here, 1972, that's this category, we're going to plug that in here. So 32 over 52, 1972 minus 1960 plus 18. And if you work that out, it becomes this. Okay. So, and if you read the problem, I didn't do this in the beginning, it's the percent that lost their population. So we had this many lakes without trout, okay, in 1960, in 1950, whereas in 1972, the number of lakes without trout increased quite a bit. So the acid rain had a big impact on the trout within their lakes.